It's a real privilege. Steel Construction New Zealand, we're sponsoring this presentation. This 20 Customhouse Quay was the supreme winner at SCNZ's awards last year. There's a copy of all the finalists in this publication. Feel free to help yourself if you haven't got a copy. Just a little bit about these awards. They're open to any project in New Zealand that's constructed by an SCNZ steel fabricator, and anyone in the design team or the construction team can enter. So entries are open. If you want more details to enter the awards, you can find it on the SCNZ website. So it's my privilege today to introduce the speakers today. So we've got Chris Speed, who's an associate at Thornton, and he was the project manager for this project. And then we have Jordan Moss, who's technical manager at MJH Engineering, and was the senior steel detailer for this project. So welcome.
Thank you.
So both of us were heavily involved over a number of years in this project. And tonight I think we're kind of going to we'll go through the design of the project and not too much technical detail, and then we'll kind of talk about the early contractor engagement process and how that really worked on this project to both improve from a project management and timing and program perspective, and also cost savings, and just actually the design process itself, having the expertise in the room to kind of give us the confidence to know what we were doing. So this project, so I'll go through briefly myself. We'll go through the site and the site hazards, the client brief, building features, and then I'll talk about the start of the process of early fabricator engagement. So this site is in Wellington. It's kind of adjacent to the Wellington Waterfront. So if you don't know Wellington, this is Lambton Quay here, and that's where the old foreshore used to be. So all of this is reclaimed land out here. So the building was built on, there was an original building here before, which is the one you see in the image before this. It was a 1960s 11-storey concrete frame building, which was damaged in the, I think it was not the Kaikoura, but the Seddon earthquakes, Cook Strait earthquakes. And the client looked to redevelop the site, demolish the building, and build a new building there. It was classed as kind of soil C to D. We did some geophysical assessment on the site around that. There was some potential liquefaction under the site, or at least around the site. However, the original building had a 2-level basement under it. It was actually founded with shallow footings on a raft slab. And so during the construction of that basement, they removed almost all of the liquefiable reclamation and marine sediments that was underlay the site. So the ground conditions under the site were fairly good. Around the site, not so good in terms of kind of lateral spread issues and potential for liquefaction loads on the retaining walls and things like that. So we had to do a reasonable amount of work around the existing structure in the basement. So the client's brief was, as all clients wanted, they wanted it to be extremely efficient, read costs, and but a high level of seismic resilience, potential base isolation. So we had previously worked on a project just across the road from this with the same developer, which had looked at doing a diagrid, kind of a lower level diagrid a few years before, and he was quite interested in it. The major thing he was looking for was efficient spaces. So it's got a 12-metre kind of column-free space at the front of the building, looking out over the waterfront. The building basically covers the whole site. So the site was about 55 metres north to south and 25 metres across. They wanted it to look iconic, because it basically sits quite prominently in the Wellington skyline, on a budget, and that was going to be simple. So what we ended up with, through a whole lot of process was this magnificent 15-storey office building. So it's a base isolated diagrid building. It's got about 21,000 square metres of floor plate, all composite construction, so relatively light, 125 meganewtons, which is about 5.5, 5.6 kPa on average over the floors. Has a steel diagrid frame, as I said, and so some of the things I probably won't talk about in too much detail tonight, but has composite steel floors, so cell beam construction, had concrete filled steel tubes. It has Resitec for damping of the floor plate, and we also used the slab panel method and kind of parametric fire curve design for the perimeter structure to try and reduce the amount of intumescent paint that was used on the project. The original building had this raft slab, so it was about 1,200 thick, and the new building was significantly less heavy than the old building. So we did at one point look at just reusing the existing foundations, but there were a couple of reasons why we didn't do that. One was that it was a kind of step foundation, so the original building was kind of a tower and podium with a podium at the back. The podium was founded at level 1 of the basement and was a shallower footing, whereas the main structure was on the 2-level basement founded on the marine, below the marine, previous marine level. And so that was kind of all right, but the back wasn't that good. And the client kind of wanted to make sure that there would kind of be no questions asked. So we ended up installing new piles through the existing raft slab, about 5 metres below sea level, which was it was pretty problematic. Yeah. The building superstructure, so it's a diagrid structure, so it's pretty difficult to make a diagrid ductile, and generally you don't want a base isolated building to be ductile. So we ended up, even though it's only an IL2 building, we ended up designing the superstructure for IL3 elastic loads to kind of account for providing some extra resilience and things like that in the superstructure because of the elastic nature of it. And the base isolation system was designed for 650 mils of maximum displacement and a 1 in 2,500 year event. And those events were defined using a probabilistic seismic hazards analysis of the building with kind of geophysical assessment of boreholes down to rock and all sorts of things, which there was rock on one side of the site at 50 metres and on the other side it was at 90 metres and things like this. So it was, anyway, quite a difficult procedure to actually work out what was going on under the site. Let's go into the design process a bit. So to kind of achieve a building like this with all of those design constraints and the client's desires required quite a lot of collaboration between the architect, ourselves, and the services engineer. It's a relatively tight design. The services engineer would say there's not enough space in the ceiling, a lot of holes through beams, clearance under beams and all sorts of things. So it required a lot of BIM integration and a lot of discussions about how we were going to kind of make it work. So it was open discussion and it worked very well actually because all the teams, so it was Dunning Thornton, us, Studio Pacific and E-Cubed, who had all worked together a lot before, so we had a good relationship there. We spent a lot of time discussing constructability, and that kind of comes into the ECI part of this discussion. And it also, the whole process was all about a clear communication of ideas. So we were passing on a lot of information to them. You know, we'd never designed a base isolated diagrid before. There are about 3 of them, or I think there's one other one in the world in Japan, but it required a lot of discussion of, at the concept stage, we used made a lot of use of things like SketchUp. So a lot of the initial work on the project was actually done in SketchUp to try and show what we could do with angles and things like this around the building. So in the end, this was the isolation plane. So These are the base isolators. So we went for an all steel grillage. So in base isolation, you have the base isolator moves, shears across, and so all that axial force has to, you get almost no P delta in the building above. So this building, the drift in a 1 in 1,000 year event was something like 0.15% drift, but you get all the drift down the bottom, so you get large P delta at the bottom. So half of the P delta from the whole building is taken out in the steel grillage at the ground floor, and half of it was taken out into the foundation structure. So a lot of the fabrication down here, these are 800 deep beams, haunched, heavy welded steel beams, and then there was a lot of integration with the lift pit, because the base isolators at the bottom of the lift pit were at the bottom of the level 2 basement. So it was quite a complicated thing, but and part of this was because we were trying to shoehorn this building, make it as efficient as possible, i.e. biggest floor plate as possible, whilst fitting it into an existing 1960s basement. So we had to kind of achieve all our clearances to the existing walls and things like this, while still trying to push the building out as far as possible and not having the diagrid 1.5 meters in from the glazing, where it would be quite a hindrance. So the superstructure is your traditional diagrid. The difference in this case from what you see in, say, London or New York, where these are used, is that we had to design for, even though it was base isolated, significant seismic forces. So the ULS base shear of this building was about 0.23 G. So pretty high, basically, what you'd design a normal building for in Auckland. And you have, it's noded every third floor, but you can still get inter-node modes of excitation. And obviously the mass of these floors still needs to get braced up to the nodes so we can take it down. So it effectively is a diagrid with a moment frame around it. So in these floors, these are all moment connections, bolted end plate moment connections, and then you've got the diagrid working in behind, taking the load down every third floor. And it was still, and so the moment frame still had to be relatively stiff. So all the perimeter beams are 16 UB sort of thing, moment frame. So relatively heavy construction. But when we got through the design, a lot of the stuff ended up, the requirement for those 16 UBs ended up basically being what we required for vibration of the floor plate anyway. So it was kind of like, even though it seemed heavy for one thing, it was quite, it needed to be there in the end, which made us feel better. So we did a lot of work initially looking at base isolation, composite columns, Resitec, looked at a lot of precedent structures. So these are kind of just some excerpts from some of the work we did initially. Trying to crimp ideas, basically, of how we could fabricate this thing, so we could put some ideas together. So we had a lot of discussions with Kevin at SCNZ, which is invaluable, Hera and Charles Clifton here at the university, who all of whom provided a lot of expert advice. And also we talked to other consultants. I think I talked to Becca about the Resitec and these sorts of things. And so we've got quite a few examples. I think the one I ended up crimping off the most in the end was there's the nodes from the Gherkin in London. Relatively simple. We were looking to use tube columns. The architect liked them. Concrete filled, they become very efficient. So basically this is what we ended up doing in the end, except in their structure it's only got a tie force around it, whereas we had a moment connection the whole way around. So we went through that concept design process, and we kind of made it clear to the client at that phase that we needed to get a fabricator on board to provide both some input on costs and also to provide some input on how we were going to fabricate these heavy plate construction, because we were talking about 40, 50, 60, 70mm plate in some locations. So at the kind of this is where I got to in my design when we kind of started engaging with with MJH, and we put forward both these options to them and said what one's going to cost the most and which one's going to be the most easy to construct. And so there were two options. One was that this one's the end plate connection, and then there's the shear plate connections. This is kind of like a BRB type connection, a whole lot of angles bolting around it. This is your moment end plate. We had to fit all the bolts inside the tube. This one to me seemed a lot more simple. I was kind of like wanting to do this one, but it ended up being about 40% more expensive apparently. And so just put this in your mind, because you'll come and see where we got to in the end when Jordan goes through his talk.
Cool.
There we go.
So as Chris said, we at MJH got involved relatively early from a contractor point of view. Normally we would be getting in theory, a coordinated set of structural drawings to work from. In this case, we were involved at sketch days, working off hand sketches and SketchUp models and things like that. From our point of view, there's a huge benefit for us being involved right from the start. Not only around the pricing, which I've outlined there first, we can price based on an accurate shop drawing model rather than guessing and working off a structural set of drawings, doing a manual takeoff, estimating plate quantities and things like that. We can work exact and we can nest things and we can really be efficient with our material usage. The key benefit for us is that we can, every project, no matter how well designed, how well coordinated it is, there's always issues. And that in itself can really hamper a project's progress. In this particular case, typically I would write a RFI and it would go through a whole process, through the contractor, to the consultants, back through the process, and it takes weeks. In this particular case, I'd be on the phone to Chris, we'd talk about it, we'd have a solution, we'd quickly document it, and then it was done. So with a complicated design like this, we managed to get through a lot of what would seem like minor issues, but can take a lot of time, and got through them really, really quickly. The other key benefit for us is we can incorporate some of our efficiencies that we've learnt over the years from various different structures. Obviously, we build buildings all the time. That's what we do. We're full-time welding. We're full-time erecting steel. So we learnt over the years good ways of doing things, what works, what doesn't, things that generally a structural engineer may not know. We were able to bring to the table some of those efficiencies. On this particular project, it's a highly technical project from a steel fabrication point of view. I've got some key fabrication considerations that we took into account. These are probably just scratching the surface, but the key one was the geometry and tolerance control. Because of the selection of node that we ended up going with the end plate design, basically from ground floor all the way up to the roof, we had zero tolerance. We had end plate to end plate all the way up, and so you can imagine even if it's only 1 millimetre out of line at the ground floor, that gets amplified as you go up, and if we had 1 millimetre per floor, we're well outside our tolerance by the time we get to the roof. So we put a lot of effort into working ways to control that tolerance and to control the geometry. This building has a very subtle curve to it, and when you break that across many nodes, some of these are out of plane by about 1 degree, less than 1 degree, and we had to make sure that was perfect. So as a structural steel fabricator, normally we're working to plus or minus 1 mil, 2 millimetre. In this particular case, we had our fabricators out there working down to tenths of a degree and less than a millimetre. Because of the nature of the project too, it was very heavy in fabrication, and it was very quick to erect on site. So we had to manage our fabrication resource to try and get a lot of work done to meet a very short erection timeline. And to put that in perspective, it's probably about a 10-to-1 ratio. It would take 10 times longer to fabricate something than it would to put it up on site. And it was a very short, initially very, very short, It got a bit longer, but very short erection timeline. So that was quite a complicated aspect in itself. As Chris mentioned, we ended up going to the end plate method for connecting the columns to the nodes. So that in itself raised an issue about how we bolt these things up. Obviously, part of the nut ended up encapsulated, or part of the nut or bolt ended up encapsulated inside the column. So we had to figure out a way to incorporate those nuts without having being able to weld them, because they were high strength nuts. We also had some quite serious considerations around the design of the connections because of the lamellar tearing issue. We had very, very heavy plate welding, and a lot of it, and obviously that introduced quite a high lamellar tearing risk. So we managed to introduce some nice design features to reduce that and to reduce the need for specialist plate. Secondary to the encapsulating the bolts and the nuts, with 10.9 grade nuts nuts and bolts as we end up going with, they have a maximum. Well, we investigated what the maximum heat input we could put into these things, and we did a quick experiment with welding on the end plates, and we found that the heat input was just getting too high. So we had to come up with a method to control, when we were welding on the end plates of the tubes, how to control the temperature in the nuts and to reduce the temperature of the nut without affecting the weld itself. So I'll go into a bit more detail on that shortly. On geometry and tolerance control. So as Chris mentioned, early days, we were working from very, very rudimentary drawings and SketchUp models. It's better than most jobs, put it that way. But what we did from there is we very early on developed the essential geometry of the building in Tekla, our structural modelling, structural steel detailing package. This gave us the best opportunity to make sure we knew what we were doing early on. We knew what our tolerances were, what our angles were, very, very down to fine detail, and we were aware of what sort of tolerances we would have to achieve right from the outset. We did a lot of evaluation and design, I guess, coordination with the nodes. As you can see, the top on the top left there, that's Chris's initial SketchUp model of the node, and on the bottom here is the final Tekla model of what the node ended up looking like, with a lot more extra detail, slab edge plates and tubes for edge protection and things like that. But you can see there was a lot of design iteration that went along. We ended up deciding that we had to machine these things. So obviously, as I said, we had very, very little tolerance. Typically we would work to plus or minus 1 millimetre. In this particular case, we decided that 1 millimetre was too much, and so we were going plus or minus half a mil. And that in itself raised extensive discussion internally, and the outcome of that was that we would be machining. Because of the geometry of the building, these nodes ended up having to be using a 5-axis milling machine to mill the surfaces, and that in itself raised a lot of complications. Myself and Malcolm, the owner of the company, drove around the North Island trying to find a machine shop that could machine these things because of the size, and unfortunately we couldn't find anyone that gave us confidence they could actually do it. So we decided in our own method that we do things, we'd buy a machine and we'd learn how to do it and we'll figure it out. So that's what we did. Malcolm flew over to Minneapolis and went into an aerospace factory there where there was a machine that was up for sale, and decided on the spot he would buy it. And within, I think it was 8 weeks, that machine landed back at MJH and we assembled it, and then we figured out how to machine these nodes. That in itself was probably the saving grace of the project. We were able to machine these things to within a tenth of a millimetre and achieve full contact bearing connections for these end plates, both on the tubes and the nodes, and control our geometry as we went up. So we knew as we were going, we were always going to be correct. It's just a couple of drawings and snapshots from the model. So obviously the left, that's the final Tekla model. I was the steel detailer, so this is my bread and butter. This is what I produce day to day. There was 12,500 drawings ended up for this project to fabricate it. There was about 5,500 man hours on my part alone just to draw it. So
I had to check them all.
yeah, and then Chris had to check them. They were right, of course. As Chris showed earlier, this is the base plane. That in itself raised significant design tolerance control issues because everything is moment end plated and there is zero shimming in that one. So we had to design and work out fabrication methods to stop things like weld shrinkage, which can be significant in these types of connections. As it turns out, we managed to fabricate this over, I think it's, 60 metres? Not quite.
55.
55. That whole frame fitted up perfectly. So that in itself was an achievement. There was a lot of sweat off my brow when that one got finalised.
It was so perfect actually that when they erected up to this level of the diagrid, it became plain that the builder hadn't actually installed the isolators at the right level because they all lifted up to flat.
Yeah,
and they had gaps, like air gaps.
Yeah, this structure was so rigid, and by the time we bolted up all these connections, it lifted the base isolators up to meet them. So obviously welded on
so
structure.
the building actually was spanning the whole length, 55, because it's basically a truss, so it was spanning the whole length without actually needing any support. So.
The reason I put this top right up here is this, at the moment, doesn't give you much of a sense of scale, but this is at ground level. This is one of the more complicated nodes that we had to come up with. I've got a photo coming up to show you this on our milling machine, but that particular assembly from the underside of the bolts there to the connection plane is about 3.5 metres high. As I say, geometry intelligent control. The essential geometry developed early in Tekla was the saving grace for the project. It gave us everything we needed to know. Machining, so obviously the full contact bearing surfaces was a good driver for the machining. We also had to leverage our other fabricator network to learn from other people. There was some significant welding, and we had to develop weld procedures and joint types to reduce the amount of shrinkage. To put that in perspective, it's very easy for a full penetration butt weld to shrink half of its root gap. So on some of these big connections, we've got a 6 mil root gap, so easily you're losing 3 mil. And we're trying to fabricate to within half a mil. So there was a lot of knowledge that went into how much controlling shrinkage and allowing for it and then fabricating around it. So there, you can see that same node. This is on our big milling machine. To put that in perspective, that table there is 1.5 metres wide. So it's a big beast. We had to override the stops on the machine to get it to work and do all sorts of things, but you can see the significance of the welding. So that's 70 mil plate, full pen butt welders. There's a day's welding there just for one guy. And how many nodes do we have? 144, I think it was.
127.
127, yeah, all up. So there was a significant amount of welding. As I mentioned earlier, we had some material property considerations to take into account. The controlling the heat and the nuts and also encapsulating them. So this top right picture is the arrangement we came up with. Essentially it's a series of plates stacked on top of each other. The nuts are held in there loosely so they can rattle around, so we've got a bit of tolerance to get the bolt in the hole, but they are fixed in there firmly so that they can't fall out. And what this allowed us to do is to pre-assemble these, check them off, make sure we've got the right number of bolts, right diameter, the right arrangement ahead of time, sign them all off, and then they got welded into the tube. It also allowed us a bit of flexibility in our bolt lengths as well, so we could, because we end up ordering these bolts out of the States, it gave us a bit of consideration for length so we could standardise them. In regards to the lamellar tearing issue, so one of the key considerations we had there was these end plates were significantly thick, up to 70 mil thick. What we ended up doing was, in a full penetration butt weld, we need to provide a backing strip to weld against. In this particular case, rather than providing a backing strip and welding to the face of the plate, we machined the edge down and provided the prep and the plate itself. This gave us two benefits. One, was that by machining past half the thickness of the plate, we reduced our lamellar tearing risk significantly to the point where we didn't need to use Z-rated plate. And further to that, it gave us a really good backing for our full penetration butt weld, so we could really put some significant welding into there, which was great. It also gave us a bit of flexibility, so obviously we were machining the node first. We would learn from the machining process where that plane was, if it was +1 millimetre or -1 millimetre. We could extend or shorten the column to suit that. So that detail gave us a lot of flexibility there. The bottom right, that shows our arrangement for controlling heat in the nuts. So because we had a significant amount of welding and a lot of heat input, we needed to reduce the heat. So we designed this water jacket. So this is some aluminium plates with some aluminium bolts. And basically what we ended up doing was using aluminium to suck the heat out of the nut and into the water jacket. And so that was dumping the heat out of the nuts, but that didn't affect the weld. So it allowed us to really pump in the weld and put some high heat into there while keeping the temperature of the nuts below 300 degrees. We also had thermocouples in the bolts that we made so we could monitor the temperature and make sure they didn't exceed the temperature we had found as being the upper limit. So from a side erection point of view, like I said earlier, it was a very, very quick timeline. So we had to come up with a method to achieve that timeline. There were several aspects which gave us the opportunity to put this thing up quick. Firstly was that we were doing what we call a jump floor methodology. So we would stand 3 floors of columns, as you can see in an A-frame, and that would be completed, all fitted out at that 3rd level, and that level would be poured. And then we would carry on building from level 3, or sorry, in this case level 2, up to level 5, while the lower floors were being infilled with ComFloor and being poured with concrete. So we ended up having simultaneous workloads happening. Typically we would erect 3 floors of steel, and then 1 floor would be poured, then we have to wait for the next floor, then the next floor, and then we can carry on up. So this allowed us to keep going up well ahead of the concrete pouring below. In this particular case, it was good that we could pre-assemble the A-frames on the ground. So we had 2 site teams. One was just set up to pre-assembling on the floor slab below on a jig that we made up so we could control the geometry, while the other team was picking up the previously pre-assembled item and putting it into place. That in itself formed a very efficient method for doing it. One, obviously we've got 2 work faces once again, but the key thing was that we could control the geometry on the ground before it was up in the air, tying up crane time. We knew it was right when it was going up. And as I said earlier, we allowed for no shimming between the nodes and the columns all the way up the building, so 15 floors of hard fixing. But the perimeter beams, the 610 UBs, which are all these ones which are rusty, we allowed a shim gap in those, and that allowed us to provide a bit of flexibility with the A-frame to set the geometry while not affecting the structure. Back to Chris.
Yeah, so let's kind of cover off some of the real benefits we saw from a design perspective was, working with a quality fabricator with their full involvement in the design process. What you're always trying to do on jobs is, particularly when you're working with contractors, is to find ways to create incentives to work collaboratively and to work productively together, rather than the scenario where people are just looking for issues and finding variations and spending a whole lot of time on things that aren't very productive. Apart from obviously, some people can make some money off that apparently, but it's not very fun. So having people involved early on makes them part of the design process, and then when you're finding MJH, they wanted to do the end plates, so then they had to make it work. So at the beginning they said, oh, we want to do the end plates, they're going to be great. I said, I don't want to do the end plates. they're going to have bad tolerance. And so they went through this whole process of working out how to do the tolerance, and it ended up with a better project in the end because of that. The varied expertise brought into the project, reduces things like institutional blindness, on both sides. So, we work in a design world. We're a relatively medium-sized company. There's only 25 of us, and we have a certain level of experience. And so you can always go down, make decisions based on previous ideas that aren't the right thing for a project. So it's always good to have people with different backgrounds involved. Our relationship with MJH, we've worked with them for a number of years, and that it's based on mutual respect. We work on, luckily we have similar clients, and so we've got to work with them for years, and it's been a great collaboration. And also, having someone involved early on gives me, as a designer, the confidence to present innovative solutions without knowing that I'm the only one that's going to have to solve them when they don't turn out perfectly. As Jordan said, the key to this kind of thing is open communication. You have to be able to pick up the phone and talk to someone about your issues you're finding, or and also giving praise when people have done good work. It improves efficiency. I got Jordan to basically do all my documentation for the building, and maintaining a productive relationship, solution. Sorry, I have to read this again. So the communication provides, so your solution rather than conflict focused. So I think we only had about, I don't even know why you sent me some of these, but I think I only had about 4 RFIs in the job, so he was probably in a bad mood that he sent those through. But the whole thing, there is a concern from a client's perspective of engaging in ECI and things like this, that you're kind of reducing the competitiveness on a project. There is great value in it, and I think it really can reduce risks, and particularly when you're talking about the margins and potential variations in that you can get in competitiveness between contractors or whoever. The risks on a project, particularly of this complexity, far outweighs any potential savings you're going to get from using someone who's 2 or 3% cheaper. So, kind of in conclusion, project was very ambitious from the client's perspective, complex site, and we kind of, we really pushed towards an innovative structural solution. It kind of, you had to do a diagrid for a base isolated building like this. It had to be that stiff. The early engagement was critical to the success of a project like this. Provided a broad range of technical knowledge, and it gave us confidence to get through the project. Yeah, do you have anything else in conclusion to say?
No, I agree totally. I mean, from a fabrication point of view, as I say, we tend to get into projects later than we would like. The documentation's never complete. It costs more money in the long run. We have to guess, we have to estimate. We can't foresee every problem, and if any problem we do foresee, we have to allow for it in some way or another, generally financially, and that has a risk on the project itself. So by being involved, particularly with a good client as well, who is willing to mitigate risk by financial, putting his money in where his mouth is, that really helped in the process.
So, and they prefer it if the documentation's even less finished. So. So these were some of the people involved. Newcrest, in particular, Lincoln Fraser, who's based up here. He is basically a structural engineer, architect, and services engineer, all combined. Amazing client. MJH, Studio Pacifics, or E-Cubed, and the geotechnical engineers. We had amazing peer reviewer from Jeff Sidwell at Oricon, and a whole lot of input from people in the industry. I think we have a quick video, and we might take some questions.
Don't need the music.
We've got any time?
Yeah.
Yes, we have some time. So does anyone have any questions for either of us? Or?
Can you talk a bit about the rattle zone on this sort of tight downtown site?
Yep. Yep. So it was a bit more difficult on this project because of the existing basement. So the existing basement was largely built to the boundary of the property, but it was it kind of incorporated the existing columns from the original building, which is a concrete frame building. So it was quite thick, and then incorporate your seismic gap, and then the diameter of the node, which in this case was 1300, 1400 diameter. So you're talking about the start of the diagrid, potentially being 1.5 meters or 2 meters in from the boundary. And you can imagine, and this was what was discussed early on, was we have to pull in really far at the ground floor, but the architect and the client wanted it to be, the diagrid to be right out at the facade the whole way up, and the facade needed to be near the boundary. So they wanted us to angle the whole ground floor out, which would have created huge issues with tying of the nodes into the floor. So we kind of resisted that as much as possible and waited until they came up with some solutions themselves. So as you can kind of see, this front edge is curved. So actually the only point that we got close to the original boundary was right in the middle at the front of the curve. And also on the north and south ends, they ended up adding a kind of shading element, which brought the building in from the boundary a bit. But, and then at the back, there was adjacent buildings on the boundary, so we ended up having a space there. So it worked through design rather than like forcing it to work. But a couple of things we did end up having to do was that the nodes themselves, we just couldn't get enough rattle space with the existing walls. So we ended up cutting pockets out of the walls and then putting retaining over the boundary. So the client we had to apply for a allowance to be over the boundary from the council, and there was a bit of work around moving of services and things like that down there. Huge problems with the groundwater and things like that because it's reclamation, so it's basically a pile of gravel, so it's extremely permeable. So any change in the groundwater level was pretty difficult to deal with. Also, we had quite a lot of concerns about locking the piles into the raft slab too early, because the other issue with the diagrid, one of the only real issues with the diagrid, is they're so stiff that, as I said earlier, if you don't get the piles properly loaded, you just will never know where the load transfer is underneath it. And so the concern was that if we locked the piles into the basement before we finished construction, the gravity load would just go, it would be much stiffer down on the raft slab than at the back of the building. And because the load can just transfer right around the building, it's basically like a box section tube, you'd lose track of where your gravity loads were. So there was we ended up having to leave holes in the basement, which kept on filling up with water.
Well, we didn't, the piles weren't tied into the perimeter until a certain level of the building was on.
It was like the 11th, we'd tied in at about the 11th floor.
And so when we provided an arrangement underneath the base isolators so that we could, I don't know if we did it, someone else did it, jack the whole building up. So if there was any differential settlement, that we could allow for that by jacking the building up and then grout filling underneath the base isolators.
So the whole building was kind of braced with friction only until it got to about the 11th floor, and some dowel action, I think. So that was a complicated aspect of the diagrid. Yeah. Right.
Thank you very much, Chris and Jordan, for the excellent presentation. Two questions. Number one, what was your ULS and SLS interstory drifts? And number two, how did you manage your glazed curtain walls, horizontal seismic movement in relation to the interstory drift of the building?
Yeah, so this is why I'll only ever design base isolated diagrids ever again, is that the SLS drift, I think, was 1 millimetre per floor, which is a 4 metre floor. I don't even think it was that. And the ULS, and that's 1 in 1,000 year, I think was 12 millimetres. So not only was there almost no displacement in the curtain wall, so the curtain wall is just a standard unitised system, so it's got some movement capacity within its frame, but also it's got a split transom, so it allows movement in the split transom. So it's hung from the floor above and pinned at the floor below. But even jib internal walls and things like this, we had no seismic heads or anything like that. We had vertical movement heads because it was cell beam structure and relatively prone to being saggy and bouncy. But
Did you allow for ULS seismic movement of the curtain walls?
I think it was inherent in the system because it was just so, the displacement at ULS was less than what it would be for a normal building at SLS. So I think it was done by Thermosash, and I think they've tested their systems up to 20 millimetres, so it would be about twice, have capacity twice what was actually provided at ULS. Yeah. So and that's one of the main benefits of base isolation, but also a structure like this is you just are limiting your the damage to your building. The issue we have is 650 mils of movement in Wellington. You're still getting relatively high accelerations, 0.25 G, as opposed to look on with GLSE of some of the buildings, base isolated buildings in Japan that are designed for 0.05 G and things like that. The seismicity is just very large, and you're limited by, in this project, that any more displacement, we're just losing the floor area. So it's a building that still has significant reduction in acceleration on the floors from a traditional building, but the main benefit is that the interstory drifts are just absolutely minuscule. So your damage to partitions, all of the kind of fit out items is just extremely reduced from your 2.5% drift frame building or